My name is Sergi Castella. I'm your co-host. I work for Zeta Alpha, and with me I have my co-host, Andrew Yates, a professor at the University of Amsterdam. Few words?
Yeah, so I'm a professor at University of Amsterdam. I work on information retrieval, particularly with neural methods, so similar to what we're talking about today.
Great. So what brings us here today? What is the paper that we wanted to discuss?
So we have this paper, The Curse of Dense Low-Dimensional Information Retrieval for Large Index Sizes. So this is about how some approaches for information retrieval, dense retrieval approaches, which I think we'll get into, don't perform as well as the index size becomes larger, it seems.
Great. Yeah, so this is a paper from Nils, Reimers, and Iryna Gurevych. I'm probably not pronouncing that right, but sorry about that. And I wanted to discuss a little bit why we chose this paper. So let me give a bit my flair of it. So this is a very short paper, only like 4 pages, I believe. Something like that. It's pretty digestible, and it explores this interesting question to me, at least, which is how, like Andrew said a little bit, how dense retrieval is, like performance scales when the index becomes really large, right? And I think this is interesting because we see a lot of research in data sets that are not that large compared to like a web crawl, like something that maybe Microsoft or Google are working for. And I found it quite interesting to explore this question of like, how do these models sort of scale? Because I do think that probably in the industry, it's quite important, right? When you scale these indexes to very large sizes.
Yeah, definitely. And one point I would add is that these collections, they're always the same size when we work on it, right? Mm-hmm. So we have a collection, the size isn't going to change. Yeah. So we study it with that fixed size.
So it's static. Yeah, actually they include some interesting experiments in the end. I hope we're gonna get into that add noise to the index and see what happens. That said, shall we get into it?
Yeah.
Cool. So why don't you start by giving a bit of like a short intro of like dense retrieval versus sparse retrieval, like BM25 and stuff, and why they're called as they're called, basically. Like why their names are sparse.
So these two terms, dense and sparse, refer to the size of a vector you would use to represent a query or document. Mm-hmm. The idea is with sparse retrieval, so this is methods like TF-IDF or BM25, we maybe have a large vector. So this is the size of the vocabulary. Maybe we know of 30,000 or 100,000 terms, so it's quite large. But it's sparse in the sense that most of these entries are 0. So many terms that we know about just don't appear in a given document. So it has many 0 entries.
Yeah.
And dense is kind of the opposite of this. So we have maybe a much smaller vector. In practice, we do maybe a few hundred dimensions rather than tens of thousands, 100,000. But these dimensions are all non-zero generally. So it's dense in this sense that every dimension carries some information.
Yeah, okay. Yeah, that's useful. No, I was asking because I remember back in a few years ago when I knew a bit about machine learning and I started reading some stuff about information retrieval, and they were talking about sparse and dense retrieval. And I understood like what was like keyword based, right, retrieval, but I didn't quite understand why it was called sparse, like what that came from. But I think you mostly answered that, right? It's like,
this is a good connection I think to make, right? It's keyword retrieval because these non-zero elements would correspond to keywords that are important, right?
Exactly.
You have a document that says neural, so you have a non-zero element, for that neural keyword.
Yeah, exactly. Yeah. But I just thought it was important thing to point out. So a second thing I wanted to ask you is like, I think there's a pretty clear distinction between dense retrieval models are often machine learning models, as in they use data to learn and are parameterized and you learn, right? Whereas sparse models like BM25 are normally not learned models, right? They're like based on like heuristics or like
historically based on heuristics like TF-IDF maybe. There are also some new learned sparse representation models, I guess a bit far from what we're going to talk about today.
I remember you mentioning that. I'm not familiar with that, but I hope that maybe someday we can get into that. But overall, we could say that sparse models are for what we're going to talk about, are not learned, right? Or TF-IDF based, and dense models are learned. Basically. Yeah. Cool. So could you maybe dive into the main gist of the paper and start going through the theory of it, so this paper gives some context, right, provides some theoretical analysis on this idea of how often like false positive documents will pop up in the dense retrieval settings, and then they do some empirical examples. Empirical investigation.
Yeah, exactly. So maybe we start with the theory.
Yeah, exactly. Let's start with that.
Yeah. So they have two proofs. The first one is essentially about how the probability for false positives increases the larger your index is. So, the more false positives you have in your index, the more likely it is that you'll encounter a false positive. Is essentially the gist of this, I think. Yeah. And this also applies to the sparse indexes, right? I think there's nothing about this proof that's specific to the dense retrieval setting. It's more just general, I think, about...
It's pretty generic that, like, if you have, like, a very small probability of many things happening... Well, I don't know if... now this is a bad metaphor, but, like, a very small possibility of something bad happening if you try... many times it's going to happen at least once.
Yeah.
It made more sense in another context. Anyway, forget about that.
So I think if you say like there's any chance of something bad happening, right? There's a non-zero chance. The more chances you have at this thing happening, the more likely it is that it's going to happen once, right? So if there's any probability,
exactly, okay. So the way I like to imagine it, and that I don't know if it's a good sort of analogy, so maybe you can tell me that, is this idea that embedding space, like you embed like documents in a low-dimensional space, in the order of hundreds, right? Dimensions. How I imagine it is like if you put too many documents in there, it's going to become too crowded. So it's like it's going to kind of be hard to differentiate between them. Do you think this is a good kind of intuition to characterize this, or like is it mislead? Like
I think it's a good intuition. This is also how I would think about it. I mean, I think these are hard to think about in general, and I'm not totally convinced that I have found the best way to think about it. But this is also what I would say, right? I mean, as a human, if you want to pick some dimensions yourself and try to categorize some documents into each of those dimensions, right? At some point, you would have too many documents for whatever system you came up with to continue working.
So I said something which was dense retrieval, right? Embeddings embed documents in a low-dimensional thing. But this low-high dimensional terminology might be a bit confusing. So what is low dimensionality and high dimensionality in the representational kind of context?
So it's hard to draw an exact threshold here. But when we talk about low dimensional, I think we normally mean hundreds of dimensions, maybe 1,000, but not 10 or 100,000. I think it's generally what we mean.
So we would say normally like dense representations are low dimensional, quote unquote, whereas sparse representations are high dimensional or very high dimensional? Would you even say that? Or?
I mean, I would generally just call them sparse, and to me, this conveys the idea that we have some dimension that is related to the vocab, and so it's probably very large. But I mean, so dense maybe 768 or 1,000, 128 around this area is pretty normal, and then sparse, it's related to the vocabulary size. So with BERT, it's something like 30,000 different word pieces. With actual tokens, it's going to be larger because there are more tokens than word pieces here.
Okay, makes sense. So it would make sense that following this intuitive level, right, that if you have sparse representation that has like 30,000 components, you run out of space. It takes much longer to run out of space in the feature space than when you have a few hundred, right, dimensions. Exactly. You have much more space to work with. And then if you even go back to thinking about what you would do, you can just increment these dimensions whenever you see a term. And this is what something like BM25. That's a good point, actually. Can you when you're working, when you have a system that's keyword-based retrieval, can you add vocabulary on the fly or like without the need of?
Yeah.
Do you know how those things work?
So I think if I follow right, this is both like the biggest both advantage and disadvantage here. You can just arbitrarily add any vocab term you want to queries and documents, right? Apple releases a new product tomorrow with a totally new, name. If this appears in documents, it will be found for someone who puts it in the query. So it's fairly easy to expand the vocab in that sense, right? Each term is just an ID. There's nothing, you don't know anything about the term semantics. It's just you've added a new term ID.
Yeah, but the sorry, maybe this is a bit like going into the, but like if Apple releases a product, right, that has a name that does not have the full name is not a token or it doesn't have an ID, it's just gonna get split into subwords that have IDs, and this is how like the backend of the the backend of the keyword search will handle that.
So this is going to depend on the tokenizer. I think it would be more common to do something closer to white space tokenization. So handling punctuation as well, but not into these character engrams that something like BERT would use.
I see.
So you would have a new token potentially, right? Like the iProduct.
You could literally have
it's just totally new token.
Okay.
But then that's the disadvantage. You don't know how, iProduct relates to any other token, right?
Yeah, absolutely. Yeah. So like they say iProduct is orthogonal to iProduct 2, right?
Exactly. Or iPhone.
Okay. Yeah. Sorry. That was a bit of a detour. Going back to the theory aspect of it. What do they show in this paper about probability of false positives?
So this first proof, they show that as you have basically more opportunities to make a false positive, you will make more false positives, essentially.
Okay.
And this, like I said, applies to both sparse and dense indexes, right? It's just general about false positives.
Yeah.
I think the second proof is a bit more related to this dense retrieval scenario specifically. I don't think we want to go through it line by line, but basically the gist of it is as you have more dimensions, you have a lower chance to make these false positives. Okay. So the probability of false positives decreases as the number of dimensions in your representation increases. So if you think about something like sparse representations, these have a much higher K. They're also constructed differently, which probably has something else to do with your chance for false positives that's not captured by this specifically.
Yeah. Okay. So something we can cut this if you're no, but something that I don't quite understand is how I guess that this what is interesting about this probability of false positive is how sharply it increases as index grows, right?
Yeah.
Do you have any good way of giving a sense of like how sharply it increases, right? Because I think, like you said, it's pretty obvious that it has to increase, right? As you, it has to decrease the probability of a false positive as you make the space bigger, right? As you increase K.
Right. I'm not sure that it's easy to characterize because it may depend on the type of embeddings and also the independence assumption. If we have multiple relevant documents, so now we no longer have that. They make an independence assumption. If we have multiple relevant documents, it's hard to say to me how this interacts. Right? Maybe even though we're making a false positive with respect to one relevant document, it wouldn't be with respect to others. I'm not really sure. But also, I don't think these vectors are created independently and uniformly distributed. It's
in the real world, right?
I mean, they're corresponding to something that's relevant or not.
Of course.
And I think this is going to inform how the vector.
Yeah. I think that's an excellent point, right? Because in the one of the core assumptions of the theoretical analysis is that there is one fully relevant document and one and the rest of the corpus is irrelevant, right? So there's like a completely binary fashion, which is the case sometimes in the real world. It is the case sometimes that there's only one thing that is the good answer to a query and the rest are no, like completely none. But there's a lot of other scenarios where you have a more graded sort of relevance of, a group of documents is relevant to a query. more than a single.
Yeah, you might have a more like information-seeking or exploratory query where many documents will do the job. If you're looking for a specific email or something, only that one item is going to satisfy what you're looking for.
What are the? I think that's interesting. If you could, so what is the name for when you're or name or examples or whatever, like when you have a query that that has a specific target that is kind of known or something?
Yeah, this can be a known item search. Like if you have something in mind that you're looking for again, this could be known item.
Yeah.
You could also have a navigational query. You're looking for a specific website. You're Googling a domain name. So this sort of thing happens. And then maybe also you want the very best information. I don't know exactly the scenario where this would come up, but this is what we talked about last time. With MS Marco, there's kind of this assumption that you're looking for the very best answer that you could get.
So in MS Marco, as a reminder, a lot of the queries are not known item, right? But the way the annotation works is that only one document is labeled as the most relevant, where in fact there's probably like a more general pool of documents that are quite relevant to that query, right?
Yeah, exactly. So it's not known item, and then the information could be found in multiple places, but it's a sort of different task where the best item is what you want.
Yeah. No, that's so this theoretical analysis sort of like mostly applies to you would say like it applies to the case of known item search or like these sort of queries.
Yeah, so this is performed thinking about one relevant document. It isn't totally clear to me what happens when we try to remove some of these like independence assumptions and add multiple relevant documents, but it's definitely performed in that setting, right? Yeah, so like we were kind of hinting at earlier, if you have other relevant documents, that may help the problem just to begin with, because now you have several chances to find the right document, right? Even if you swap one ranking, you still have some others that may work out.
Yeah. Absolutely. So, maybe to close off this discussion on the theory part of things, like to what degree do you think this theoretical analysis is valuable or gives you any insight on the problem?
Yeah, I think it's very interesting that to relate this size of the vectors, this number of dimensions, back to the index size, because this I don't think has been done previously. But it's also theoretical in the sense that it doesn't really tell you what's going to work well. So more dimensions, it's better to have more dimensions. But it's hard to say, what's the point where it matters, or if you change the embedding space in some way, maybe fewer dimensions is enough, right? It's very general.
Yeah. I mean, like you said, one of the assumptions that this proof relies on is that the vectors are independent and uniformly distributed, right? And this is certainly not the case for a lot of embedding models where it's been shown, but that they tend to occupy only like a subset of the space of the embedding space, or like they're not. I think it's called anisotropic or something.
Yeah, and anisotropic.
Something like that. That means that they're only like sort of using I think like a cone-shaped subset of the embedding space or something like that.
Yeah.
So that probably makes it worse, and it's kind of hard to know how this interacts. And basically, the theoretical part of the paper doesn't sort of include any of that.
Right. And maybe one last thing to add, if you think about sampling vectors randomly, I think it's pretty obvious that the more vectors you're sampling randomly, the more danger you're in, because eventually one is going to be close to that relevant document.
Absolutely, yeah.
But here we have the encoder, right? The vectors come from reading text and an encoder producing the vector. So the vectors themselves are not random. And so this has to do with the properties of the encoder in some way, right? Is it going to put them in the right places?
Absolutely, yeah. I mean, this relates like if you have there's going to be like some distributional, there's going to be a relationship between the distribution of documents and the semantics of the vectors, right? So in exploratory cases, exploratory queries, you would expect that whenever there's a false positive, it's it's not really it's not necessarily a false positive. It might just be the annotation is.
Yeah.
Well.
So actually, this just makes me realize there's kind of two kinds of false positives here. One is if the encoder, for lack of a better word, thinks this is relevant, right? Is it encoding it into the right space? So maybe it looks relevant. It's not, but it puts it in a reasonable place in the embedding space due to the fact that it looks relevant. And the other is if you have something that doesn't even look relevant, where is it in the embedding space, right? So we have both the encoder could make some mistake about where a document should be placed.
Yes.
And then that document's vector could also lead to a false positive, ultimately.
Yes.
So I guess I'm saying even if the encoder makes the right or wrong decision, right, it's trying to put it in some space, for lack of a better way to say this. Even if it's deciding that correctly, you still can have false positives just from this issue.
Yeah. I
mean, if you have a spammy document, right, the encoder may try to put it, in a region of the embedding space where it will, be relevant to that query. But that's not a problem of the index size or the embedding space, right? This is the encoder is encoding the document in a way we don't like, essentially.
Should we jump to the empirical part of the paper? So what do they do to explore this question from the empirical side of things?
Yeah, so they have that theoretical proofs, and then from the empirical side, they set up some experiments. The first one is with MS Marco. This is the data set we talked about a bit. Basically, there's, on average, just one passage marked relevant for every query. So what they do is they start from these relevant passages. So they say it's about 7,400 relevant passages for 6,980 queries. So you see just slightly more than one on average. They start from these passages. They index them, and then they look at metrics as additional passages are added to the index.
Okay. And these additional passages are
not relevant passages. So
they're just picked. Do you know if they're picked at random from the because so to give an example, I think all of the tables that they show are pretty similar, right? So you have on the model side of things, you have BM25, right? And then they're compared to trained models of different dimensionality, right? You have 128, 256, and 768 dimensions. And then you see different index sizes, right? 10,000, 100, and then up to 8.8 million. So in each of these index, for each query, you have one top relevant passage.
Right. So it's one relevant passage, and then they randomly select some other passages to get to their target index size. So the first setting is they start with about 7,400 relevant. They add about 2,600 to get to an index size of 10,000.
Okay. Interesting. Yeah. All right. And so what do you think is the main takeaway of these first experiments?
Yeah. So I guess the takeaway is that as the index size increases, their performance is decreasing. And it's decreasing a little bit less as the number of dimensions increases. But I guess it's also not a huge difference. So it's usually 768 dimensions is a few points better than 128 in this experiment, right? So to give you a sense of how much it decreases to the people listening. So we start at 89 MRR, 0.89. At index size of 10K with 768 dimensions. And then this drops to 17. So 89 to 17 is a very large drop when you go up to the full collection. But comparing, say, 128 versus 768 dimensions, there's always a small decrease when reducing the dimension size. So it's something like 89 versus 87.5 at 10,000 dimensions. And then with the full collection, 8.8 million, it's something like 17 for all the 768 dimensions versus about 16 for the low number, 128.
But from glancing at this table, to me, I was talking about table 1, it doesn't look like the dense retrieval has hit a threshold where this is a substantial problem, right? Because it's still substantially overperforming BM25, for instance, at all of the index sizes, right?
Yeah.
So do you think this means that that this is not a problem, like that this false positive rate is not a problem yet in this case? Or
it could be. It's hard to tell. And another factor here that makes it difficult is that you're always adding non-relevant documents. So just from the first proof, we know that even with a normal, inverted index, it would become harder as you're adding more non-relevant documents.
Exactly. Like it's just harder to find a document out of, a million than 1 out of 10. Like,
if you randomly sample, you'll be okay with the 1 out of 10. Yeah. So it's hard for me to separate those effects, but I agree. It is not the case with their better training where they use hard negatives that they ever drop below BM25's performance.
Yeah.
Yeah.
Actually, that makes me think: is there a technique or like an easy way where you can compare models across different index sizes in like a fair way, so to speak, or quote unquote, or you know what I mean? Because like you just said, like the bigger an index is, the harder it is going to be to find the top relevant document because just there's more of them.
Yeah. I don't know if it is possible across index sizes for a given method. Right from our first proof, we know if there's any chance that you can have a false positive, you'll just have more false positives with more chances.
Yeah.
It follows pretty easily. Yeah.
But you don't have any works in mind that explore this kind of question?
Not offhand.
Because basically you can compare MRRs across. So imagine I told you, right? They have 2 models, but I only have results on 2 data sets. On one is on a partition of MS Marco that's 10,000 documents, and the other one is on a partition of MS Marco that's a million documents. So if I ask you the question, which model is better, A or B, and you only have MRRs for the 10,000 and the 1 million, could you, what I mean? Is there any sound way of doing apples to apples on that?
I don't think there's a sound general way of doing any sort of apples to apples things there. If you know a lot about the collections and the methods, you might be able to come up with something. So maybe this kind of transitions to the next experiment. Because, with BM25, they don't have this issue may not necessarily appear as much. And in the next experiment they don't have this issue at all with BM25 because what they're doing is just generating new terms to add to the document. And because of how BM25 works, if you have a new term that's never appeared before, BM25 has 0 chance of making a false positive mistake. And that's what you see, right?
Yeah.
But without understanding what's going on with things like that, I don't know how to make a fair comparison. I would say you need multiple index sizes and metrics from all the methods you're interested in on the different index sizes, and now maybe you could start to get at it.
Yeah, you could get. Yeah, okay. No, that's fair enough. I can see how it would be extremely hard, but I can also imagine how it could be relevant in a context of not academic research, but you're a company, you only happen to have 2 benchmarks of 2 models on similar data sets but happen to have different size or something like that, right? And you want to make a quick assessment of which one is overall better or something like that.
Yeah. Maybe if you had some idea of the trend that you would expect, maybe you could make some guesses like this. Yeah. But
anyway, so I think we can jump to the do you want to jump to these experiments they do with random strings, or is there anything else you want to comment?
Yeah, I think the random string one is good. I kind of hinted at it already.
So what do they do here?
Yeah, so here, rather than in the previous experiment, they started from an artificially small collection, right? Only the relevant passages, and they expanded this all the way to the full size collection. Mm-hmm. So they added everything in they had. Here, they're interested in basically looking at larger indexes. So that means they need a new way of enlarging the collection because they've already hit that 8.8 million barrier. Mm-hmm. So what they do is they generate essentially random strings and create documents from these. I'm simplifying a little bit because they look at also another method, DPR. Okay. With this DPR, they also take some pre-existing titles, like Wikipedia titles, as documents rather than completely random. But the point is they generate a random string, or they're taking a Wikipedia title from somewhere, basically creating new documents and seeing what happens as they add a lot of these new documents in. And this is interesting, I think, because they should never be relevant, right? A random string is useless. But actually what they see, despite the fact that they should not be relevant, is that these random strings are sometimes ranked higher than the relevant document. And this is their metric. So they're looking at how often some random string is above the correct document in the ranking.
Yeah, that's fascinating, right? I mean, that you would throw a bunch of random letters there and that they would pop up. Right?
And so for BM25, like I said, they never pop up.
I mean, you could still imagine a case in which, if you have a monkey typing for infinite amount of time, it's going to write any book or something like that, right?
Definitely.
So, I guess if you wait long enough, these random strings are going to happen to be a important keyword.
I think exactly. When the random strings are keywords or high IDF keywords, then they'll start to matter for BM25. You probably would have to generate many more.
Just for clarification, it doesn't happen. Like here, they have 100 million documents, right? Random, and they seem to have 0.00 MRR. So
0.0 instances of the random string being ranked higher. With BM25.
Exactly.
So they go from 100,000 to 100 million.
So
and with BM25, it never happens. Like you said, it could, but it would.
But certainly the formal guarantees are way higher, right? If you have a production system where you would, in a production system, you would never worry, like in a production system, search engine or whatever, where you have BM25, you would never worry that a bunch of, random strings are going to pop up because you can basically understand each part of the algorithm and know that that's not going to happen, right?
Yeah, exactly. So there's no way that random string could return a document unless it appears in the document.
Exactly.
Whereas with the dense approaches, that random string, has to be encoded. Now it's going to become a dense vector, and it matters what dense vector you get out, right? So this can create false positives if it happens, to be confused for the positive vector.
The thing, like normally when you train some of these transformer models, right, you clean up the data first, so you don't show them random stuff, right? Like you only show them positive samples of natural language, right?
Yeah.
So it would make sense that they don't know how to encode random strings in any way, right?
Yeah, I think this model probably has never seen something like this. Not in the pre-training data or in MS Marco, probably. I mean, you could add this to the training data, right? I mean, if you want to guard against this specifically, you could maybe add random strings as negatives.
My question, like, do you think that this is not really like any fundamental question, but like you could just guard against that by training with random strings and telling the model this is garbage?
I mean, you could guard against this specific experiment, I think, but then you could pick different distractor documents. You could take French language Wikipedia documents. None of these are relevant to an English query if you assume that the user has to be able to understand, right? So these are no longer random. So I think it's more related to how the experiment is set up. It would be hard to guard against all possible ways.
I really like that concept, the term you use, the distractor documents. Is it like a standard way of referring to them?
Sometimes. I see it more in NLP community than actually core IR conferences. But distractors.
So I love that because I think it quite relates to if you sort of make the parallel in web search, for instance. When people talk about SEO, in a sense, you could conceptualize it as like you're just trying to come up with distractor signals that are gonna trick the search engine into believing that your website or your something is relevant, right, for certain queries. So I wanted to ask and talk a bit about how this changes between keyword-based search engines, BM25, like when you basically how you create distractor documents for BM25 versus how you create distractor documents for dense retrieval, or another way that I said before is like adversarial sort of documents or so. So
for BM25, that what matters the most are these high IDF terms. So I guess if you have a query in mind, then you can construct a document that shares these high IDF terms from the query. And if all you're using is BM25, you probably can just spam the terms a lot, right?
Yeah,
like
of course,
a document full of them. In reality, web search has more signals than this, so that something more nuanced. But
Google are
they've caught on to that a few years ago. Yeah.
I would expect.
Yes. But I mean, you could, like, if you're just running BM25, that's what you would do.
Yeah.
With the dense method, it's hard to understand what to use, I think. You could take something that's sort of like a relevant document and hope that this will work, but it's hard to know how whatever the text is going to be represented in that dense space, right? So you almost need to. I would want to try it a few times. Yeah, it's guessing is quite hard. If I have to guess, I would try to start with a relevant document, and try to tweak it in some ways that makes it non-relevant.
Yeah. Are you aware of any interesting literature of like destructured documents in dense retrieval, or doing some sort of like adversarial attacks on indexes and this kind of stuff?
I haven't followed this closely, but in dense retrieval, I'm not very aware. I know there's work in like computer vision, for example, where you can have, add some noise to an image and now it, can look like something else.
And there's pretty pretty good, robust like recipes for that. Like you can use the loss function to follow the gradient towards an image that would be perceptually indistinguishable, but that has a way higher loss. So that would mean that the model is recognizing it as something else, probably, or something like that. I mean, my point is, it's not just that you can just try a million random things and eventually the model is going to fail. Is that like you can build an algorithm that consistently fools, like the model, right? Or something like that.
Yeah, exactly. And here, this would work if you're allowed to change the vectors. I think the problem is with an image, your input is continuous, so you can, change whatever part of that image you want. But with text, it's discrete, right? You're starting with some tokens. And so you can't have a vector that would work adversarially, and also necessarily maps to any token. Right, you can easily come up with a vector. So in the hypothetical example of you wanna have some adversarial attack to an index where you don't have access to the model that encodes the index, but you can upload documents, right? Yeah. It would be kind of hard because you would have to come up with a document that is like characters, right? You cannot inject a vector into that index. You have to inject a document that happens to be encoded into a vector. Yeah, I think it's absolutely doable. I think it's just a bit harder than the computer vision.
Yeah, but it's probably doable. I mean, my impression is that if this thing is deployed at scale by big players, maybe that would start happening, right? Like if Google started relying a lot on dense retrieval, which I think they don't do now, right?
I'm not sure.
Well, I don't know. Yeah. They do re-ranking, but for sure, very well. I mean, they've said that they use re-ranking.
Yeah, I think they've said they use transformers in production. A 3-layer transformer, but I'm not sure exactly what.
The point is, like, I would expect that if a big player did that, a lot of people would start trying to game the search engine. Yeah. I mean, that's what has been happening for the whole history of search engines, right? Like people trying to.
Right. I mean, I guess there's a big incentive to game it, right?
I mean, I would argue that. I don't know who. I remember seeing this point on Twitter or something that I found really good, which was how much easier it was to search for stuff maybe 15 years ago. But like most of the web was like kind of people genuinely writing blogs and Wikipedia and stuff that was useful, and versus now that is completely professionalized gaming of the information space, and then everything is like as a user you're often kind of like afraid that you're being tricked or like that you're being shown something because
much more adversarial, probably many more incentives and different incentives than originally.
Anyway, sorry, I went full on tangent. Is there more stuff that you would like to highlight from these experiments on random strings? string passages.
I think the main takeaways beyond that are similar to the earlier experiment, right? There's not a huge difference between 128 and 768 dimensions. There is a difference, like 768 has fewer false positives. But to give an example, it's like 2.7 versus 2.1 between them for 100,000 documents versus 9.7 versus 8.5 for 100 million.
That is indeed quite perhaps surprising, right? I mean, something that would, in my mind, sort of validate these hypotheses that dense vectors get too crowded would be if there was a very substantial difference between the 700 versus 100, maybe. I don't know what kind of difference I expect. Even I mean, there is a difference, but it's not. Exactly,
it's not overwhelming the difference between index sizes or something. I guess is one way to say it.
Exactly. I mean, in a sense, it's like, of course, it has to be better because 128 dimensions is like, it's like a subset of 7. Like you can literally have a 768
right.
dimensions with all zeros always. And I mean, my point is like, it needs to be better. You cannot say.
It should not be worse.
Yeah,
right?
like
it should only be better.
Why would it be worse?
Yeah.
Right?
Yeah. It does not have to be worse, right? Like, you can put it that way. With all zeros, it could be equivalent.
Yeah.
But it certainly doesn't have to be worse. You have these extra dimensions that could be used.
Anyway, so what like, I don't know, takeaway would you get from these experiments?
I mean, I think they support the previous results, but I don't, again, have a good sense of how severe the problem is.
That's also
it's hard to understand.
I also have the same impression. Like I can imagine how this can severely be a problem at some point. Like, I mean, it's really easy to think, okay, if you want to embed a corpus of 1 million documents into vectors of 3 3, it's like, okay, it's pretty obvious that you're going to run out of places to put. I
mean, these are floating point numbers, right? They're not even real numbers in the sense they can keep going on
so
forever, right?
It's at some point you can literally prove, like from almost like an information theoretical coding problem, like the code length of the floats is not. But I don't get a really good sense of like where's the threshold-ish, more or less.
I don't either. I don't know how to get a good sense of that also, though. I can't think of a quick experiment to run to improve that, right? So it's not at all meant as a criticism of the paper. It's hard to figure out how to get a sense there.
Absolutely.
But I mean, this information theoretic perspective, I think, is interesting because I couldn't tell you if 768 dimensions is enough to encode the random string, for example. I'm not sure how long the random string is. I'm not sure if I missed it. But I mean, this is something that you could... Right, it could be determined.
Work out, but reaching that threshold should be really hard, right?
I mean, I think it depends on what the length of the information, right?
It should be fairly easy to calculate, right? I mean, naively, right? I mean, each character is a number of bits, and then, I mean, of course, you can compress and all of that stuff, but anyway.
Yeah. And this is also a bit different because this would be something like reconstruction. But these representations also aren't trying to be used to reconstruct the original document.
I mean, you could argue from the perspective of compression, you could argue that they're like trying to compress the document in a way that is like you extract the meaningful parts of it, but you sort of throw away the implementation details, right? Like you would not expect to be able to reconstruct the document from its embedding, but you would expect a machine to be able to make a summary that is a valid summary of that document.
I mean, it's something like a lossy image compression, maybe, right? So not exactly what you started with, but enough for your use case. So here, measuring relevance to some query terms.
Yes, exactly. No, I do really like to have this perspective of like compression to conceptualize some of these things. But anyway, okay. So the last question I want to ask you is, one of the reasons I picked this paper was because I think it might be relevant in the like long-term question of, is dense retrieval something that is gonna replace sparse retrieval? Is gonna like sort of coexist, or is sparse retrieval sort of like still gonna be dominant for most of information retrieval, and like dense retrieval is gonna be like a more niche kind of sort of. So to this question, like 20 years from now, or 10 maybe.
It's hard to predict, but what I would say is that this paper illustrates some downsides of dense retrieval to me, but it doesn't change my general feeling that this seems to be a way we can make progress and possibly improve over sparse retrieval in general setting. Mm-hmm. But part of this comes from the fact that it's hard to get a sense of how big the problem is and where the problem is, like we were just saying. So I guess we know that there's problems. This is one problem. There have been a couple others, maybe that other papers have found. But how severe it is still really an open question to me.
In a sense, I guess another way to frame the question is sparse retrieval and dense retrieval good at the same things? Or are they like good at different things in a way that are sort of complementary, in a way that... You know what I'm like where I'm going a bit, like, because okay, so let me like say how I imagine it will play out or something. Is it does seem to me that for some type of queries, sparse retrieval will always be better for maybe some of these like known retrieval where you have like trillions or quadrillions of items and you know what you want to get. Probably some sort of sparse matching will always beat the dense retrieval because you have some guarantee or some sort of like in these queries where there's one relevant thing and the rest is completely irrelevant. Whereas for other types of more exploratory queries, how I imagine it is like dense retrieval sort of is more able to capture better things when there's a bunch of documents that are relevant. So how I imagine it playing out is having some sort of long-term coexistence of these things are good at slightly different queries. So an ensemble of the two will always beat any of the.
Yeah, I mean, I think that very well could be. They're definitely complementary right now, I guess. And the question is, to what degree dense retrieval will be able to become better at the sorts of queries that sparse retrieval is good at. So, for example, a term you haven't seen before, or maybe known item search, these sorts of issues. So if you have a SKU number, like a product number, 10 digits, they're just random numbers, you're looking for this product. Sparse retrieval, something like BM25, will find it easily. With dense retrieval, this really, I think, would need to be represented as something like a term ID. You don't want many semantics happening here, right? There's not a lot you can say. It's a product number. So maybe it will advance to the point where these sorts of things can be handled better, right? Maybe this can just be matched exactly as a token rather than trying to understand, the semantics of that token, which I think is going to fail. But right now it seems very complementary. I wouldn't want to use a dense retrieval method for something like that. Yeah.
And if you have to make a bet, let's say, okay, let me make it more concrete. In 10 years' time, is Google gonna, is dense retrieval gonna be part of the, Google's or Bing's or like one of these big web search?
I think it will definitely be part of it. Whether it totally has replaced sparse retrieval, I'm not sure. I think it will be a part of it, and if I have to guess one way or the other, I would guess that maybe there are ways to overcome whatever limitations, and dense retrieval will, be able to handle things like these, unique terms that don't carry much meaning.
In general sense, like the slightly negative or gloomy kind of gist of this paper is not like you would say is not too too convincing to believe that there's very severe limitations of.
I would say that it points out things to be aware of and to keep in mind and be concerned about maybe, but it doesn't, to me, show how severe or not severe they are. Like, this is still an open question to me.
And I mean, to be fair, I believe that the scale of, I mean, they're showing here scales of, 10 million documents, like for the vast majority of applications of information retrieval, that's plenty, right? Like that's, I mean, if with 700 dimensions and at 10, you're not hitting a regime where this is a severe problem, for most applications out there that are not like large scale web search, it's fine, isn't it?
Yeah, it seems like it. It's but also maybe these applications don't have the adversarial angle, right? It also depends. If you're looking at an application where you can have adversarial users, this may complicate it quite a bit.
Absolutely. We'll see. We'll see how it plays out. But it was definitely an interesting thing to think about and to read about.
It's a very interesting paper, I think.
I don't know. Do you have any other closing? I think that we should close it around here. But do you have any other remarks, conclusions? I don't know. Maybe some other pointer that you thought of that.
I'll just point out another paper that they also mention, which is this Luan et al. Paper, Sparse, Dense, and Attentional Representations for Text Retrieval. The reason I point it out is it's related in the sense that they look at how increasing the length of a document you're going to encode can increase the chance of false positives, right? So moving from, one sentence to 1,000 sentences. Clearly, that 768-dimensional vector cannot, take an arbitrary number of sentences. At some point, your compression is too lossy for it to work.
Of course.
So, like a different angle of similar,
And what do they have any like proposal of like? For instance, is there any? Okay, this is maybe opening a bit of a can of worms that we should cut. But is there like any sound wave of designing like a vector to a set of vectors distance function that is like you encode the document with 10 vectors instead of one, and you do some sort of distance of quick distance or
so I don't actually remember exactly how the method this paper proposes works, but it's along these lines. So if you have a document that's 10 times too big for your vectors, you can encode it in 10 different ways. And ideally, each of these encodings would probably be emphasizing some different aspect of the document, right? You could just chunk it into 10, passages. But if you think about something like a long Wikipedia article, maybe you want to combine certain passages together that are topically similar.
But you can always do I believe you said in MS Marco document track, what they normally do is that you just do search in passages and then you assume that the document that the passage is in is relevant. Right? Or something like that. So you can get around the problem by just always, having a passage as your unit rather than a long document. No, that's fascinating. So could you maybe, before we close, give us, what does it mean for a document to be too long for a vector? Like, how do you formalize that idea?
Yeah, this is hard.
Well, maybe
in the paper,
it's too much. We can leave it for another.
A quick example of what they do in the paper. They have a theoretical type of embedding, not word to vec or BERT or something, but a theoretical embedding type, and they analyze how this theoretical embedding performs as the documents become larger. So they can say, for this type of embedding, you need it to be, at least 1,000 dimensions, 10,000 dimensions, whatever, in order to capture a document of some size. I don't know, 1,000, 10,000, I'm not sure, with a low chance of having a false positive.
Okay, so it follows a similar,
it's not, it's kind of a similar experiment, but a different concern.
No, that's interesting. Yeah, maybe we can discuss that at some point. Definitely fascinating to me.
Yeah.
So, closing remarks?
No, it's a great paper, I think. I'm very curious to see how this will play out in the future, right?
Absolutely.
How does this, the index sizes affect things?
All right. So thanks for listening, and I'll see you in the next one.
Yep.